Well, look at that. Oh man. Thanks. Thanks, YouTube. I'm sure YouTube did that. They pretty much nailed it on that one. All right, so we're gonna talk today about using a definite integral to calculate the length of a curve. All right, so that's gonna be a little bit weird, but we're gonna get started anyway. All right, so what do you need to know before you get started? Number one, you need to know the Pythagorean theorem. The second thing you need is spaghetti. I'll tell you here. I'll tell you why in a second. So, how could you find the length of this random curve? It'd be nice if you could just grab the ends and like pull it straight. So, if you said like get a piece of string, lay that string on top of it, kind of follow the curve around, then pull that string taut, measure the string, bada bing, you win a prize. Go ahead and make sure you hit that subscribe button before we go any further. Hit the notification bell so you get complete access to all the Eric Purvis calculus information. That was really bad. I'll get better I'll get better the next time. But what if all you had was spaghetti? What if all you had was spaghetti to find the length of that curve? Like not like cooked spaghetti, okay? Like straight spaghetti. Like what would you do? Well, you could, right? Just like take the spaghetti and align the beginning and the end. Right? There you go. Boom. That piece of spaghetti gives me an estimate for how long the curve is. Not very good. Right? So you could also, you might be thinking, well, I could like break the spaghetti and just kind of line up those little breaks all along the whole entire length of that curve. I got tired of doing it, but you could see the idea that I could just it's not the best, right? It's closer than just one piece of spaghetti from the beginning to the end. Okay, with that in mind, you're probably thinking, well, make the spaghetti pieces infinitely small, or like as small as I can make them, and then just lay those pieces there if I could make them infinitely small. Well, then that all those spaghetti shards would line up with the curve exactly. Then I could piece them all together back into one long spaghetti noodle and then measure that long spaghetti noodle. Well, that would be great, right? That'd be great. That would give me the length of that weirdo curve exactly. So that little mental experiment is how we're going to do things in the world of calculus, finding the length of a curve on a certain interval. We've already talked about how to find area between curves. So this is the perimeter. Let me say that again. This is the perimeter portion of calculus, like the geometry, area, perimeter, volume, right? But we're going to do the same thing here in Big Idea 5. So let's talk about how we're going to do this with functions and calculus. So how do you find the length of a function on an interval? Spaghetti? No, not quite. All right. So here's how we're going to do things, right? We're going to just kind of think about this smooth, yeah, curve. Now this smooth curve, we could find the length of this curve, right? By laying these little straight red lines here, L sub 1, that line, while it's not on the curve, if I could lay a bunch of those little lines along the curve, it would reasonably estimate the length of that curve. Now, how would you find the length of that little segment? Well, the little triangle here that I've drawn gives us an indication of how we're going to do it, right? So you can think distance formula, but there really is no such thing as a distance formula. It's just a Pythagorean theorem disguised. So we have some change in x and a change in y, and we'll just Pythagorize it. So we'll say that L sub 1 squared is delta x sub 1 squared plus delta y sub 1 squared, and then square root. So here's what we get. We get that to segmentify the curve, right? That's a word now. We're going to just segmentify the curve and use Pythagorean theorem to find the length of each segment. Here we go. The length of any segment is just the square root of the change in x squared plus the change in y squared. Now, I've got those little sub i's, which should feel really familiar. Okay. So then we just push some symbols around. This is not necessary for you to do later on, but it is necessary for you to see. So don't skip ahead in the video. Don't do that. This is where the formula comes from. So here it is. We got delta x sub I squared plus delta y squared. Got it, all square rooted. Now I'm going to factor a delta x sub I squared. All right, so this is what I would get if I did that. Now, that allows me to pull the delta x outside of the square root, and also this delta y squared over delta x squared. I'm going to make that one quantity squared, so it looks like that. All right, so the square root of 1 plus delta y over delta x, a quantity squared, and then delta x sub I is sitting outside of the square root. So yeah, that thing right there. That looks familiar, doesn't it? That looks very familiar. Delta y over delta x is slope. It's the slope of that little segment. Now that segment is not on the curve, right? And if we're trying to find the length of the curve, how are we going to use things that are not on the curve to find the length of the curve? That seems a little bit like it doesn't balance out. Well, here's where the rub. Here's the rub. That delta y over delta x, because this curve is smooth, right? Because it's smooth, that means it's differentiable everywhere, and that means the mean value theorem applies to all these little intervals. So I can say, using the mean value theorem, now here's all the words of it, but it just means that delta y over delta x, I can exchange that piece with, right here, f prime of some x value that is on the interval. Does that sound familiar? Should, because that's how we did definite integrals. All right, so that part you might want to look at a little bit later when I post the notes, or here you can just kind of like pause it on the screen and see what's going on there. But it's so important because of the final word there. It's so important because it puts us back in relationship to the curve. That slope, that is the slope between 2 points. The mean value theorem says the derivative at some point along the curve is exactly the same slope. That allows us to say that the length of the ith segment is the square root of 1 plus the derivative of f at some c sub I squared times delta x sub I. Now, okay, you can feel it. You can feel it if you've been paying attention in class. You can feel what's coming. We're going to add the segments together. So the length 1 plus length 2 plus length 3 plus all the wall of them, and then we can fill out these formulas here. We can rewrite that as a sum using summation notation. And then what do we want? We want delta x to be super small, and in so doing, we make the number of segments go to infinity, and kind of vice versa in our thinking here. Kind of just simple. Now, if you're like a math nerd professor out there, don't call me on that. It essentially, we want to make the number of segments go to infinity, and to do that, we have to make the delta x's get super tiny and go to 0. And gee, have I heard about that before? Yeah, that's how we did it with definite integrals. So making n go to infinity of the sum of this critter is a definite integral. So folks, to find the length of a curve, a smooth curve, f of x between a and b, we use the formula, the integral from a to b of the square root of 1 plus derivative of f squared with respect to x. And it's got to be smooth, so you can't do this over like cusps or things like that. It's got to be a smooth part. It's got to be smooth, so you could break up the curve if you had to. You won't see a lot of that, but just in case. Now, I want you, the key here is to remember where this whole party got started, and that was with the Pythagorean theorem. I know the integral final result doesn't look Pythagorean, kind of not. We get the square root thing, but we played with it a little bit. So just remember that it was the square root of delta x squared plus delta y squared. Now, it's just like taking Pythagorean theorem to its logical end and sprinkling on a little calculus. But that spaghetti curve at the beginning, remember the one that did loops and all kinds of crazy things? Yeah, so that's not a function, but we can still use calculus to find its length. Now the formula is going to change just a little bit because the curve definition is going to have to change just a little bit since it's not a function. So we're going to see that in like parametric functions that are coming later on. We can define crazy loop-de-loops, but we can still find their length using this idea. So stick this in your back pocket because we're going to use this idea later on. All right, so let me show you a couple examples and we'll move on with life. So find the length of a curve, x to the 3/2, on the interval 0 to 9. So here is a picture of what the curve, x to the 3/2, looks like on 0 to 9. So here we go. We'll just set this thing up. So just take a look over here. We get it all set up. I've evaluated everything. So we got the integral from 0 to 9, square root of 1 plus derivative of the function squared. So I got to take a derivative within that spot. The derivative of x to the 3/2 is 3/2 x to the 1/2. Square that, you get 9/4 x. Now you could do some fancy u substitution to get an exact answer, or you could throw it in technology, your calculator or Desmos, anything like that at that point. So it's a matter of setting up. If you can set these things up right, you should be able to get the right answer because that's just definite integral FTC stuff that you already know how to do. Wink. Or you can just use a calculator. Many times you're just going to be able to use a calculator for that. So here is the u substitution, just in case you wanted to know. So hit the pause button there, double check all that stuff to make sure it's all right. You can kind of follow what's going on there, the u filter and all that jazz. So now that you did that, did you remember how to do u substitution? Did it all flow? Okay, hopefully it did. It confirmed 28.728 is exactly the same as this ugly mess of fractions and fractional exponents. It is. I checked. All right, so warning. This happens to a lot of students is they're just chugging along. They remember the formula. Actually, they don't remember the formula. They misremember the formula. So they'll put f of x in place of f prime. That's what I see a lot for mistakes as far as the mistake goes on this type of problem. They just put f of x in instead of f prime. So don't be one of those people and make that same mistake. It's common, it happens, but we need to train ourselves and remember the formulas for what they are. Remember that whole mean value theorem talk that's huge, right? It's huge, right? We're not just memorizing formulas, but we know where the formulas come from because we can see the progression from Pythagorean theorem, tack on some algebra, sprinkle on some calculus, and boom, we got a definite integral. Okay. Another example here is find the perimeter. Remember the last video? Did you watch lesson 5.1? We talked about the bubble between sine x and cosine x. We found the area of that little bubble. What if we wanted the perimeter of that little bubble? Well, the perimeter of that bubble would be, okay, we use the same intersections. They're not different. All right, so then we just want to set up an integral for the top part, right? The top part is sine x. So the integral from pi over 4 to 5 pi over 4, square root of 1 plus the derivative of sine, that piece squared. But then the lower part, which probably the same, probably see that it's going to be the same. There's some symmetry things going on here, but just for good measure, that would be the integral from pi over 4 to 5 pi over 4, 1 plus derivative of cosine, that piece squared. They got the same intervals, they got the same limits, so I can actually combine those two together, which I do here a little bit later. Here I'm just taking the derivatives, which then I just popped into a calculator and evaluated. I'm not doing that by hand, so there you go. It is 7.64-ish. But the setup was the whole battle there. Okay. Are you ready for this next one? I don't think you are. Unless you watched this video before, you don't know what's coming. And if you're watching it again, thank you. All right. So we're going to find the circumference of a circle. And the circle is defined by x squared plus y squared equal to 1. So y'all know what that is. Centered at the origin. It's got a radius of 1. I mean, come on, man. The circumference is just pi times the diameter. The diameter is 2. It's just 2 pi. We think we're stupid or something? No. Well, maybe some of you. But that's beside the point. Or we could use calculus and we could find arc length using the formula we just talked about. Are you with me? All right, so we could just find that little green part and multiply by 4. That's my plan. That's my plan. Here I go. All right, so that is going to be the length of the function square root of 1 minus x squared, just from 0 to 1, so just that first quadrant piece. And I'm going to find the length using the formula. Buckle up. That's the integral from 0 to 1, square root, 1 plus derivative of my function squared. Okay, so the derivative of the square root of 1 minus x squared, we got to think about a little chain rule action. So it's going to be 1/2 chunk to the negative 1/2 times d chunk. All right, so there's that good time in that step. So there's the derivative. Neaten that up over here. Neaten that up a little bit. Square it. So I got x squared over 1 minus x squared plus 1. Well, I can combine those together using a little bit of algebra. So here we go. That's 1 minus x squared over 1 minus x squared plus, oh, wait a minute. The x squared cancel. Okay. We're getting somewhere. Well, that's 1 over the square root of 1 minus, oh, there's a pattern. The integral of 1 over the square root of 1 minus x squared is arc sine. So it's arc sine of x from 0 to 1. That's the arc sine of 1 minus the arc sine of 0. That's pi over 2. And I said I was going to multiply by 4? Yeah, I did. 4 times pi over 2 is 2 pi. Are you serious? That was awesome. How do you find the length of a smooth curve? You already know it because you heard it already. It's the integral from a to b of the square root of 1 plus the derivative of the function squared. And what are we going to do next time? Next time we're going to do volume. Okay, we've already done length and area. Of course, we need to go 3D. So we're going to do 3-dimensional calculus where you use definite integrals to find some volumes. Can't wait to show y'all that. It is awesome. Awesome. Thanks for joining me. Peace out.